Discover the hidden artistry behind transforming raw iron and steel into precision-engineered masterpieces through cutting, forging, and machining. At McNeel Steel, advanced coil processing technology ensures exceptional flatness and quality in sheet products. The company uses industry-leading stretcher leveling systems manufactured by Redbud Industries, designed to handle a wide range of steel coil grades and thicknesses. During processing, the coil is uncoiled, stretched beyond its yield point, and precisely leveled to eliminate internal stresses and surface imperfections. This method produces sheets that remain flat and dimensionally stable, even after cutting, shearing, or fabrication. Thanks to this modern technology, McNeel Steel can deliver consistently high-quality flat steel products that meet the demanding requirements of various industries, from construction and manufacturing to transportation and energy. The efficiency of the near-dry sawing method using the UNIST minimum quantity lubrication system. Previously, this EV-rising 560 bandsaw operated with traditional flood coolant, which often caused serious problems such as operator dermatitis, slippery work areas, and environmental waste. Additionally, flood coolants can contribute up to 15% of total manufacturing costs, making them both expensive and inefficient. By converting to the UNIST Coolube 2210 EP system, the process becomes cleaner, safer, and more sustainable. The MQL system precisely dispenses only the minimal amount of lubricant, required no more and no less. This ensures optimal lubrication without the mess or waste of conventional coolant systems. As a result, blade and tool life are significantly extended, reducing replacement frequency and maintenance downtime. Moreover, Coolube provides long-term economic and operational advantages. It helps preserve machine components, prevents rusting, and eliminates oxidation or sticky residue. The work environment is cleaner and safer since there is no excess coolant dripping onto floors or machine surfaces. Operators also benefit from improved health conditions, as the system completely removes skin irritation risks associated with coolant exposure. In summary, the UNIST Coolube MQL sawing method represents a major step forward in metal cutting technology. It not only reduces manufacturing costs and environmental impact, but also enhances productivity, equipment, longevity, and workplace safety, offering a modern, cost-effective, and eco-friendly alternative to traditional flood cooling systems. The direct bending of a heavy steel plate using an industrial plate bending machine. This operation is commonly employed in the fabrication of large cylindrical shells, pressure vessels, and heavy-duty components, where precision curvature and structural integrity are essential. In this case, the machine is used to bend a 56 mm thick steel plate, which requires high forming force and careful handling to ensure uniform deformation across the plate's entire width. Before bending begins, the steel plate is carefully positioned on the machine's lower rollers using cranes and lifting chains. Because of its substantial thickness and weight, manual handling is impractical and unsafe. The plate edges are inspected to confirm that there are no cracks or surface defects that might propagate during bending. The material is typically carbon steel or alloy steel with a yield strength suitable for cold or warm forming, depending on the required curvature radius N. The plate bending machine used here is a 3-roll plate bending machine, consisting of 2 lower rolls and 1 upper roll. The lower rolls are fixed and supported, while the upper roll moves vertically to create the bending force. The rolls are made from hardened alloy steel to resist wear and ensure accurate bending even under extreme pressure. Hydraulic cylinders control the position of the upper roll, allowing for precise adjustment during bending. The operation begins with initial pinching. The steel plate is inserted between the top and lower rollers, and the upper roller is lowered to clamp the plate firmly. This ensures proper grip and alignment. Once clamped, the plate is slowly fed through the rollers, while the top roller exerts a downward force, gradually bending the plate into a desired arc. The process may be repeated several times with incremental roller adjustments to achieve the final curvature. For a plate as thick as 56 millimeters, pre-bending is an essential step. The edges of the plate must be slightly bent before rolling to avoid flat spots at the ends. During pre-bending, the plate is positioned so that only one end is gripped between the rollers. The top roller applies localized pressure near the edge to create a uniform bend. After one side is pre-bent, the plate is rotated 180 degrees and the other side is treated similarly. This ensures the final cylinder will have a smooth curvature without straight sections. Once both ends are pre-bent, the plate is passed completely through the rollers for final rolling. The operator carefully adjusts the roller pressure and feed rate to achieve a consistent curvature along the entire plate length. Depending on the machine's capacity, the bending can be done cold or with mild preheating. In cold bending, the force required is higher, but the plate retains its mechanical properties. In contrast, warm bending involves heating the plate to 100 to 250 degrees Celsius to reduce yield strength and facilitate forming, minimizing internal stress and the risk of cracking. Throughout the process, the operators monitor the plate's movement closely to ensure symmetrical bending. Any misalignment can lead to an uneven radius or twisted shape, especially in thick plates. The bending radius is measured periodically using templates or digital curvature gauges. Adjustments are made as necessary to correct deviations. The The bending of a 56 mm plate demands enormous power, often several hundred tons of hydraulic force. The machine's structural rigidity and roller diameter play crucial roles in determining the achievable thickness and bending radius. For example, thicker plates require larger roller diameters to prevent localized deformation and to maintain consistent contact between the rollers and the plate surface. Once the desired curvature is achieved, the upper roller is raised, and the bent plate is carefully removed from the machine using cranes and lifting chains. The curvature is checked again for dimensional accuracy, ensuring the radius and roundness meet the required specifications. After this verification, the two ends of the bent plate are aligned and welded together to form a complete cylindrical shell. The welding process is carried out using submerged arc welding or MIG welding, depending on the material and thickness. Proper alignment is ensured using clamps or tack welds before the final weld is completed. After welding, the joint is visually inspected and may undergo non-destructive testing such as ultrasonic or radiographic inspection to verify weld integrity. The welded cylinder is then stress relieved through heat treatment if required, ensuring that internal stresses from both bending and welding are minimized. The Gildemeister CTX is a highly versatile CNC turning center designed for precision, reliability, and automated machining operations. Developed, the result of the partnership between Gildemeister and Morisaki, this machine represents a perfect blend of European engineering and Japanese innovation. Available in different models, such as the CTX 310 and CTX 310 Eco, the series is widely recognized for its outstanding accuracy, stability, and productivity in modern metalworking industries. One of the CTX 310's most notable characteristics is its rigid and vibration-dampening construction, which ensures consistent precision even under demanding cutting conditions. The high-quality cast-iron bed provides excellent thermal stability and reduces deformation, allowing the machine to maintain tight tolerances during long production runs. This makes it ideal for manufacturing complex components in industries such as automotive, aerospace, and mechanical engineering. The CTX 310 is also distinguished by its high degree of automation, which minimizes manual intervention and increases operational efficiency. It often includes driven tools, enabling both milling and drilling operations directly on the lathe. This capability transforms the machine into a multifunctional center, reducing the need for multiple setups. Additionally, the automatic tool changer, typically featuring 12 tool positions, significantly shortens non-productive time by enabling quick, precise tool switching. For continuous and unattended production, many setups incorporate a bar loader, which automatically feeds raw material into the spindle, and a part catcher, which collects finished components without operator involvement. These features make the CTX 310 ideal for batch and serial production, where efficiency and consistency are crucial. In terms of control, the CTX 310 offers advanced CNC systems such as Siemens C-numeric 840D or 810D and FANUC controllers, providing intuitive programming and real-time process monitoring. These controls ensure smooth coordination of complex machining tasks and help operators optimize cutting parameters with ease. Performance-wise, the spindle speed can reach up to 5,000 RPM, ensuring superior surface finish and productivity. The high-speed turret allows rapid indexing between tools, further reducing idle time and enhancing machining throughput. Overall, the Gildemeister CTX 310 exemplifies precision engineering and advanced automation. It remains a benchmark in CNC turning technology, offering manufacturers a powerful, flexible, and dependable solution for high-quality metal part production. The Boast TA53H is a high-performance horizontal turning and milling center designed for machining large windmill bearings. Featuring exceptional rigidity, precision, and versatility, it handles heavy-duty components with ease. Its advanced multi-axis capability ensures accurate turning, boring, and milling, making it ideal for producing massive, high-precision parts used in wind energy systems. At Trevisan, France, a wide range of combined turning and milling machining centers is available. Trevisan's 5-axis and multi-axis machining centers are renowned for their exceptional machining quality and precision. The company's long-standing philosophy focuses on fixed part turning, ensuring maximum stability and accuracy during operations. These advanced machines integrate turning, milling, and drilling in a single setup, significantly improving productivity and reducing handling time. Trevisan's innovative design and robust construction make their combined machining centers ideal for producing complex and high-precision components in demanding industrial applications. The HMTG-17 is a hydraulic cylindrical grinding machine built for precision and productivity in both batch production and tool room applications. Known for its high stock removal rates, it efficiently grinds various cylindrical components while maintaining fine tolerance limits and excellent surface finishes. The hydraulic system controls table traverse, wheel head movement, and feeding operations for smooth and accurate performance. Available in two main models, the G17U and G17P, it offers flexibility for different tasks. The universal model includes a swiveling wheel head and internal grinding attachment, while the production version uses a larger grinding wheel and higher power. Automated cycles simplify operation with single lever control of key functions. The Yorky Type O grinding machine is a heavy-duty cylindrical grinder designed specifically for oilfield and industrial applications, such as grinding carbide-tipped stabilizers, motor sleeves, mills, and drill pipes. It is capable of performing both internal and external cylindrical grinding, ensuring high precision and consistency across large and complex components. This machine is available in manual or CNC-controlled versions. The CNC models are equipped with FANUC control systems, which provide superior accuracy, repeatability, and easy programmability for complex grinding operations. Depending on the setup, The Yorky can accommodate a large swing of up to 44 inches and features a standard bed length of 120 inches, with optional extensions reaching up to 33 feet, making it suitable for long and heavy workpieces commonly found in oilfield tool repair and manufacturing. A distinctive feature of the Yorky is its 12-inch hollow spindle, which enables the precise grinding of extended shafts and tubular components. The standard equipment package includes incremental infeed, precision ball screws, digital AC drive motors, a coolant system, and a tailstock-mounted dressing unit, all of which contribute to smooth, accurate, and efficient operation. Engineered for durability and performance, the Yorky Type O ensures high material removal rates while maintaining fine surface finishes, making it an essential machine for companies specializing in oilfield tool refurbishment and large cylindrical component production. Whether operated manually or through CNC automation, the Yorky grinder offers outstanding versatility, precision, and reliability in demanding industrial environments. The cut-to-length line 2200 by 20 mm is an advanced automatic system designed to uncoil, level, and cut heavy steel coils into precise flat sheets. The process begins with loading a steel coil onto the decoiler, which securely holds and unwinds the coil at a controlled speed. The strip then passes through a straightening and leveling unit that removes internal stresses and corrects any curvature to ensure flatness and dimensional accuracy. After leveling, the steel strip moves to the measuring and feeding section, where it is accurately measured according to preset dimensions. The shearing unit, equipped with high-precision blades, cuts the strip into sheets of the required length with minimal burr and high consistency. Cut sheets are then automatically transferred to the stacking system, where they are neatly aligned and stacked on pallets for easy handling. This fully automated line is capable of processing steel up to 2,200 mm in width and 20 mm in thickness, suitable for carbon steel, stainless steel, and other metals. The automation system, controlled by PLC, ensures synchronization between all stations, reducing manual intervention and increasing productivity. Overall, the cut-to-length line delivers high-quality flat sheets with excellent surface finish, dimensional accuracy, and operational efficiency, making it ideal for steel service centers and manufacturing industries. PV Pipe specializes in manufacturing high-quality straight-seam submerged arc-welded steel pipes under the EOS technology. The company produces pipes ranging from 106.4 mm to 1,524 mm in diameter, with lengths from 8,000 mm to 200 mm, and wall thicknesses between 6.4 mm and 35 mm. All products comply with international standards such as well as customer-specific requirements. To achieve the strict technical specifications of the API 5L and related standards, PV Pipe employs a modern and fully integrated production line featuring 3-roll forming and submerged arc welding with advanced automation. The production line includes 18 processing and inspection stations to ensure consistent quality throughout every stage. The process begins by feeding steel plates into an automated line where CNC cutting and edge beveling are performed. The plates are then formed on a 3-roll bending machine to ensure accurate roundness. After pre-forming, the pipe edges are tack welded, followed by internal and external saw welding using 4 automatic torches with a precise positioning and monitoring system. This advanced setup minimizes time, reduces costs, and guarantees weld accuracy. Subsequently, the pipes undergo visual, ultrasonic, and X-ray inspections to detect any welding defects. Dimensional calibration ensures correct diameter, roundness, and straightness. Each pipe is then beveled, hydrostatically tested, and rechecked by automatic ultrasonic and magnetic particle inspection systems. Random samples are selected for mechanical, chemical, and metallographic tests in the company's modern laboratory. PVPIPE's operations are certified under ISO 9001-2015 and fully comply with API and safety management standards. Supported by skilled engineers and technicians, the company guarantees reliable products for heavy industries. On November 7, 2018, PV Pipe marked a milestone by signing a memorandum of cooperation with Shear to enhance international collaboration in pipeline manufacturing and services. The production process of iron and steel components at Hatakiyama Ironworks is a detailed and highly controlled series of operations that transform raw steel materials into precision-engineered parts. The process starts with the arrival of raw materials, where billets are delivered to the factory. These materials are carefully checked for surface condition, size, and chemical composition before being approved for production. Once inspected, they are transported to the cutting section for the next stage. The sawing process involves cutting billets of predetermined length using high-speed bandsaws or circular saws. These cut billets become the basic workpieces for the forging process. Sawing must be performed accurately to minimize waste and ensure consistent weight for each blank onion. Following cutting, the billets are moved to the heating furnace. They are gradually brought to the required forging temperature, often above 1000 degrees Celsius, to increase plasticity and make them suitable for deformation. Uniform heating is essential to prevent internal stress or cracking during forging. N. Next comes upsetting, a process in which the heated billet is compressed axially between dies or anvils to increase its diameter and refine its internal grain flow. After upsetting, setting down adjusts the shape by reducing certain sections to achieve desired profiles or step-down diameters. The operation proceeds to solid forging, where the metal is shaped by mechanical or hydraulic presses into the approximate form of the final product. During cogging, repeated deformation refines the grain structure and improves mechanical properties by elongating and reducing the cross-section. This is followed by scarfing, a surface cleaning operation that removes oxide scale and minor cracks caused by previous heating. N. To aid deformation and prevent sticking, coal is added as a lubricant, forming a protective coating between the hot metal and forging tools. This black layer also reduces surface oxidation. The billet is then turned around to ensure uniform working on all sides before continuing with hollow forging, where a central cavity is formed using a piercing mandrel or punch. Hollow forging is used to produce parts such as tubes, rings, or bearing housings. After piercing, expanding enlarges the inner diameter to the required size by inserting tools or applying internal pressure. Throughout these steps, the straw boss supervises the operation, ensuring every part meets the required forging tolerances and preventing production errors. The process then moves to tap forging, in which the ends of the forged part are shaped or threaded as needed. This step often prepares components that will later be assembled or fitted with other parts. Once forging is completed, straightening is performed to correct bending and warping caused by uneven cooling. The part is aligned using mechanical presses or rollers to restore perfect geometry. Next, cutting removes excess flash or unwanted portions, bringing the part to its exact length. The product is then marked with batch numbers, heat numbers, or part codes for traceability before heat treatment. Untitled. Heat treatment is one of the most important stages in the entire process. It begins with normalizing, which involves reheating the forged part to a specific temperature and air cooling it to refine the microstructure and remove residual stresses. Tempering follows, in which the metal is reheated to a moderate temperature to increase toughness and reduce brittleness. Then comes quenching, a rapid cooling process in oil or water to achieve the desired hardness. After quenching, a second tempering step is often carried out to balance strength and ductility. After heat treatment, the part proceeds to grinding, where surface imperfections are removed and high precision is achieved. Grinding improves roundness, flatness, and surface finish, ensuring that the part meets dimensional accuracy requirements. Following this, run-out measurement checks concentricity and rotational balance, while dimension measurement verifies all geometric tolerances using calipers, micrometers, and coordinate measuring machines. Next, the product undergoes non-destructive testing. Magnetic particle testing detects surface and near-surface cracks by magnetizing the part and applying magnetic powder that highlights discontinuities. Ultrasonic testing examines the internal structure, identifying defects such as voids or inclusions using high-frequency sound waves reflected from within the metal. To further ensure reliability, material testing is performed. Samples are taken for tensile testing, measuring the ultimate strength, yield strength, and elongation of the steel. Impact testing is also conducted to determine the toughness and resistance to sudden shocks. After successful inspection, each part is marked again to record test results and certify compliance with specifications. To prevent corrosion, a rust prevention process is applied. This may involve coating the part with anti-corrosive oil, applying a rust inhibitor film, or packing it in moisture-proof wrapping. Once the product has been treated and inspected, it moves to the shipping stage. Components are cleaned, packed, and labeled before being loaded for delivery. Finally, many forged components undergo lathe machining as a finishing operation. Precision lathes are used to perform turning, facing, threading, or boring operations to achieve final dimensions and surface finish.